controlled rotations of an ancillary qubit. This video describes how to perform a mapping that will encode the register containing the alpha to a sine and cosine angles in the amplitude of the ancillary qubit. Here, ket vector alpha with subscript m is a binary representation of decimal number alpha using m qubits. If alpha is a decimal fraction, then the vector ket will contain the coefficients of alpha, translating this fraction into binary format. To perform the desired transformation, one can use the effect of single qubit rotation about the y-axis. Applying Ry gate on a qubit initialized in state 0, we bring the qubit in superposition state with the amplitudes which depend on the angle theta. This is already quite close to the desired state of our ancillary qubit. Now we want the cosine arguments to coincide and 2 pi alpha to be equal to half of theta. Using the expression for alpha as a sum of coefficients, we can easily find the expression for theta. Since the alpha coefficients are 0 or 1s, the conditional rotations of an ancillary qubit controlled by each qubit of alpha perform the desired transformation. Let's look at the following example. Let alpha be 0.75, and we want to encode this number in the sine and cosine argument of an ancillary qubit. In order to represent alpha in binary form, 2 qubits are required, and each of them should be equal to 1. Now we can calculate the angles which are required for 2 conditional rotations. The first is the rotation of ancillary qubit conditioned on the first qubit on the angle 2 pi, and the second, rotation on the angle pi conditioned on the second qubit. The application of the first conditional rotation is equivalent to the application of single qubit rotation about the y-axis on 2 pi. Now we apply the second conditional rotation and get some more complicated state. However, it is nothing else but the cosine of the sum and the sine of the sum of 2 angles, pi and pi half, which gives 3 pi half in total. And that is exactly 2 pi multiplied by 0.75, which we wanted to encode. The quantum circuit which performs the described mapping is shown on the screen. Controlled rotations on a certain angle around y-axis can be realized using the circuit in the green box.